talk for this evening is Dr. Justin Alsing from the Centre for Computational Astrophysics. I'll make it short.
Okay, thanks for bearing with us. Oh, I've got a laser pen too. Okay, so since Catherine gave us such a nice overview of the state of cosmology and of weak lensing, I'm also going to talk about weak lensing, and that's put me in a ghastly position where I could either try and match Catherine and give another nice overview of cosmology and weak lensing, or I'll do something really ghastly and actually talk about the guts of what goes on under the hood when we actually do weak lensing. So that's risky. I might lose some of you because this stuff is really dirty. But I'm going to try and give you a flavor of, see if this works. Do I push it? Pull it down? There we go. So I'll try and give you a flavor of why weak lensing data analysis is so hard and why there's been so much suspicion in the community at large about it. And then I'll try and give you a flavor of how we actually extract cosmology from weak lensing surveys, at least in the way that I personally think about it. And I'll try and show off some of the cutting-edge cosmological data analysis techniques that we're using, where we're doing these monster analyses inferring 1 million parameters all at the same time, which sounds mental, and it is a bit mental. So if the only things you take away from this is weak lensing is really hard, and we're really mental for trying it, that's fine. That's fine. Okay, so I think the movies won't work. Let's see if it does. No. Okay, but we have a picture. That's just as good. So let's just recap what weak lensing is all about. So as light propagates from some distant galaxy through the universe on its way to us, the light gets bent around the intervening matter distribution, like this, as we've seen already. So what that means is the shape of the galaxy that you observe is going to be distorted. Okay. So that distortion, so that lensing signal, so that's the change in shape that you see on the galaxy, is going to be some integral of the large-scale structure, so the integral through that 3D cobweb through the universe. And it's also going to be a function of geometry, okay, because this really is lensing. It's just as though God is playing a prank on us and put a gigantic 10 megaparsec lump of glass somewhere out there that is bending the light. The maths is broadly similar. So it also actually probes the geometry over these cosmological distances. So if we can observe this lensing effect, it contains a whole wealth of cosmological information. So the large-scale structure that we see, it's seeded from those initial conditions, which is more or less this lumpy map that Catherine showed, which is these lumps and bumps that arose in the very early universe. And then they evolve under whatever gravity theory we have. So if we want to go beyond Einstein, the assumptions you make about gravity go into how the large-scale structure forms over time. And the nature of the contents, so the nature of dark energy, and the nature of dark matter, and the nature of neutrinos, and all sorts of stuff. So this is a really powerful probe of things that we're really interested in. So how do we do this in practice? So if we can measure the lensing effect of millions or tens of millions of galaxies in a large volume, then we can use that to actually reconstruct the distortion field in 3D. And this distortion field, as we've seen, contains all of that lovely information that we want to get our hands on. So it contains information about how the structure is formed over time, the gravity theory, what the contents of the universe is. So I'm going to be talking about basically how do we make these measurements and how do we get here. Okay. So one thing I just want to really emphasize is that we can make these maps of the distortion field, but this is a realization of a random process. Okay, so the structure in the universe is seeded from these little quantum fluctuations right at the beginning of time. Okay, and that is a realization of a random process. So just having this map alone doesn't really tell you much. It's really the statistical properties of that map. So a given cosmological model will tell you how lumpy and bumpy this thing is meant to be, or how many big voids you're meant to get, or are you going to get big, long, stringy bits, or little lumpy bits or whatever, as Catherine told us to. Good. So what do we actually measure when we do weak lensing? Okay, so we have these big, wide surveys, and we're scanning as bigger volumes of space as we can, and we get some optical images. And frankly, they're rubbish, right? We have tens of millions of them, but they're all really rubbish, okay?
That's a really good one.
That's a really good one. Yeah. Like, you won't get that. That's like, you might get this one on Christmas Day. And then you get an email the next day like, no, only kidding. So they're really, really rubbish. And then we also have fluxes. So we do the observations in a few bands. So we get a few colors, basically, for each galaxy. So somehow, we're meant to measure the shape of the galaxies from these rubbish images, right? Which is going to be really hard. We'll discuss that. And we're meant to measure the redshifts from just a few colors, right? So in general, this is a hard problem. So let me just try and give you a flavor of why these things are individually very hard. So let's talk about shape measurement just briefly. So let's think about what takes us from this beautiful, beautiful galaxy that's sitting there trundling along through space-time, minding its own business, to this dirty thing that we actually observe. Just talk about the process that takes us there and which things we need to account for in order to go from this to having a measurement of the true shape of this thing. So it gets lensed, right? So the galaxy is sitting there far away, and it's going to be lensed by the intervening matter distribution, okay? As we've heard, this is a tiny, tiny effect. This is a 1% effect, okay? So for those of us that want to do precision cosmology with weak lensing, we need to measure the shape to much, much better than 1% if we want to do really hardcore precision cosmology with weak lensing. If we're going to actually, resolve this level of change of shape. Then the thing gets convolved with the PSF at the telescope, okay? That also changes the shape, sometimes quite substantially. So you need to know this really well. Same with the atmosphere. The atmosphere is going to mess things up. And other instrumental artifacts that happen in there, depending on your chip, can mess things up too. So you need to know these things really, really well so that they don't contaminate this tiny 1% effect. And then we pixelize it, and then you get a load of noise in there as well. And noise is a pain in the ass because it makes things rounder. So it doesn't just make it noisy, it actually also changes the shape as well. And that's really annoying if you're trying to measure a 1% change in shape. So we need to know the noise properties really, really well. And all of these things can vary in time, they can vary over the survey, they can, there can be all sorts of nasty stuff going on. Galaxies are also ugly most of the time, okay? This is nice. This is basically a circle, right? Anyone can tell me what the shape of a circle is. It's just a squash circle. This thing, how do you even define a shape for this thing? Okay, so we don't even really have a good forward model to tell us what's underneath the clothes here. What does the naked image really look like? So that really limits our ability to build a really good model for this process, to take us from real galaxies to these noisy images that we have. So that means we're always going to get biased results when we do shape measurement, which we need to carefully correct for. And that can be a painstaking process. And to make things even harder, a lot of the images, especially for upcoming surveys, which are going to be deep and have a lot of very faint objects, a lot of the objects are going to be blended. So this is particularly bad if you have one galaxy quite close and another one behind. So they're not lensed in the same way because there's this matter to the first one, and then there's a whole load of other matter that's lensing the further one. So if you try and measure this thing together, imagine it goes through here, and you get some noisy image, you're going to get something that's catastrophically wrong. So we need to be really good at either deblending galaxies or flagging the ones that are blended and throwing them out. So all of these things, and this, by the way, is the concise list. If you speak to someone that actually does shape measurement for a living, which there is an army of people doing, they'll give you a list as long as a Leonard Cohen song of effects that can really screw you over. So shape measurement is hard, but people are doing it. There's an army of people doing it. Catherine's one of the generals in that army, and we're making a lot of progress. But I just want to stress this is a hard problem. So what about redshift? So how do we measure redshift? Okay, so you observe a galaxy, distant galaxy. What you really want to do is take a spectrum for the galaxy, right? If you can take a spectrum, identify some features in it, and you say, oh, I recognize those things, that's, I don't know, whatever. And that should have a wavelength out here, but you see that it's shifted, voila, you've got the redshift. Easy peasy. We are not going to have spectra for any of these galaxies. Okay, we need 100 million, a billion galaxies. No way you're going to get spectra. So what we have instead is we have like 4 or 5 broadband measurements. Okay, so we have a magnitude in 4 or 5 broadbands. So we're approximating this spectrum by like 4 or 5 points. Okay, now if you're trying to measure redshifts and you go to your mate in the office next to you and you say, oh, can you give me a spectrum for this galaxy? And they'll be like, oh, yeah, cool. And he gives you 5 points. You're going to be like, 5 points? You can't do anything with that. It seems crazy. But actually we can. Some of these features are picked up and you get the overall shape of this thing. You can get redshifts from this, but again, it's really, really hard. And all of these effects from before can have a really significant impact on the redshifts that you get. So you need to know the PSF really well. The seeing is going to smear things out. It's going to screw you over. Noise can bias the redshifts that you get. It's going to be really sensitive to knowing the galaxy type and luminosity and the size distribution, which are all things you don't know. So you're going to get biased estimates that you have to carefully correct using simulations or otherwise. So there's a very long road to going from these 4 or 5 broadband magnitudes to something that we can actually call a redshift. And remember, if you get these things wrong, right, you're trying to build a map of the distortion field. If you get all your galaxies in the wrong place, it's going to be total gibberish. So it's, we're really sensitive to getting this right. This is as crucial, if not more crucial, because in some ways it's harder than measuring shapes. Okay, so doing this stuff is really, really tough. But people are doing it. There's an army of people doing it. I'm not really one of them. I'm very happy that they are doing it and that they're doing so well. But I hope that gives you a flavor of why there's so much activity in weak lensing and why there are so many people working on it, because there is so much work to be done to make sure that all the I's are dotted and all the T's are crossed in terms of cleaning out all of those systematic biases and small effects. So the second thing I want to talk about then is what happens next. Okay, so let's say, this army of scientists have measured shapes and redshifts of 10 million galaxies. And then they come knocking on my door and they say, all right, can you give us some cosmology out of this? So we're nowhere near done yet. All we've done is measured shapes and redshifts of a bunch of galaxies. So how do we go from the survey then to reconstruction of the distortion field and actually getting cosmological inference out? So the central thing that we want to get here is this guy. Okay, so what is this? This is the probability distribution for that. This is the cosmological parameters. Okay, so this is the things that Catherine was talking about. So this is like, how much dark matter is there? How much dark energy is there? What's the nature of dark energy? How lumpy is the universe? What were the properties of the initial fluctuations that seeded the large-scale structures in the universe? These are the things we really care about. What is the mass of neutrinos? And the lensing distortion field, given the data that we've observed, okay, which is now a bunch of measured shapes and redshifts. Okay, so this is actually crazy. Okay, so why is this crazy? This is crazy because this lensing distortion field is going to be every single pixel in your survey volume that you're interested in resolving the lensing distortion field over. So this is going to be like a bajillion. So we have like a bajillion dimensional probability distribution that we need to map out somehow. Okay, so that seems like a crazy problem. So I just want to, this is going to be kind of an advert for the kind of things that we're doing at the bleeding edge of cosmological data analysis, where we're actually doing this and we're getting these million dimensional posterior distributions out. So this is so big I'm going to make it huge and just make the point that if the only thing you care about is the distortion field, you just integrate this one out, okay? And then you have this guy, the probability of your distortion field, the true thing, given the data. This is everything that you know about the lensing field in your survey. And likewise, if you only care about the cosmological parameters, like most of us, then you just marginalize out the distortion field, and voila. So how do we get this thing? There's going to be 3 steps. The first step, we're going to bin up the data into a slightly more manageable form, okay? The second step, we're going to write down a model, a generative model for the data. So that's how you go from the things you care about down to the data. So that's a full statistical description of what your data is. That gives us our posterior as a function. Then we need to sample that thing in order to actually get inference out. So what do we do with the data? So here's our galaxies, all right, in Redshift as well. Okay, we're going to separate them out into a couple of Redshift slices. Here we've just done 2, but you can imagine you might want to have a lot of Redshift slices so you're resolving everything in the Redshift direction. So at the moment, we're just going to resolve kind of integrated distortion fields in these Redshift slices. Okay? We're going to pixelize it. So now we have some really noisy estimates of the distortion field across these patches and in Redshift slices. So at the moment, there is actually a true distortion field in here. You can barely see it. You can maybe just about see some features. It's really noisy, and this is for typical signal-to-noise of current data sets, or maybe even a bit better. And then there's going to be maybe some mask in there too. There's going to be bits of data that are corrupted or point sources you have to punch out. So this is the kind of ugly starting point that we're at. We have these kind of ugly, noisy, masked maps. And from this, we want to get nice, clean distortion maps and cosmological parameters. Okay. So let's write down a model for this data. How would we generate the data? How would we simulate that data if you're asked to, given a cosmological model? So, well, not much goes into that. So if you give me some cosmological parameters, then I can say, I can do my cosmology, right? And my cosmology tells me how I could generate a realization of that distortion field, okay? So that's basically just the large-scale structure in the universe, a realization of it for a given gravity theory, give me a number for the amount of dark matter, a number for the amount of dark energy, properties of the different contents of the universe, etc. And then you're going to add noise, and that gives you a realization of your data. So because we want to be Bayesian, we need to stick a prior on top too. So this is a full statistical description of the data. And the cute thing about doing this is this guy, remember this is the target, okay, is just a product of things appearing in this model. Okay, so as long as we can write down a prior, a cosmological model for how the distortion field is generated, and a model for the noise, we're golden. Okay, this is done. Problem is, still, this is a really, really high-dimensional probability density that we have to sample. So the third challenge that I'm going to cut short on, but we've made a lot of progress on, is how do you sample these things? Okay, so again, holy moly, we have this million-dimensional PDF that we need to sample. That's mental. A couple of decades ago, nobody would have ever imagined that you could even dream of doing this. But advances in Monte Carlo sampling, we can actually do this with no sweat. Or at least your CPUs are going to sweat. Or if you get too near your CPU, you're going to sweat. But we can do this. And there are a couple of implementations we have. I'm actually not going to talk too much about these. But I just want to flag that, huge advances have been made in terms of the way we sample from these ultra high dimensional PDFs. And we've done a lot of work on this in the last few years. That means that this is really a tractable problem now. I don't find this scary anymore. And that's a big step forward for cosmological data analysis. So let's just see it in action. Okay. So this is the survey that Catherine was quite attached to for a long time and put a lot of her life into. It's called CFHD Lens, and this is what the data looks like. So you can see it's really ugly. really low signal to noise, really ugly mask. These are 4 patches of sky. So it's a bit of a mess. So let's have a look at what we can get out for this. It's lovely, but yeah, it was a lot of work to get something nice out of it. But we did, and you guys did too. So this is the distortion field that we get out. So just looking back to this noisy, you can't see any structure in here at all. And amazingly, we've managed to get out, this is just the mean of the posterior, but we have a full posterior distribution for every single pixel in this map. And we have really surprisingly clean lensing maps in these redshift slices by doing the problem this way. And you can see that the variance that you get in the mask is really big compared to where you actually have data, which makes sense. So we can do this, and quickly just to look at cosmology. So this is similar to a plot that Catherine showed in terms of tension with Planck. So the red and the blue are from different analyses of CFHT lens. So the red is the one we did. The blue is one that Catherine and others did. And again, you can see, so this is from the CMB. So 2 things to note. One is that, if this was a dick swinging contest, it would be obvious who's winning. Fortunately, it isn't. And we're doing better really, really quickly. So just to show you, this is the next generation. And now this is the CMB. And this is the most recent weak lensing analysis. So already they're way more comparable than they were for CFHT lens. So, weak lensing is marching forward really, really quickly, and we're doing really, really well. So that's great news. Second thing to note, though, there is this little bit of tension, which is causing a lot of debate in the community. And, yeah, it is an open question. Who has the problem with the systematics? Or is this just a random fluctuation? And there's a lot of effort going into solving that problem at the moment. Good. I'm not going to talk about that. So weak lensing data analysis is really hard. We can do it. We're kind of crazy for trying, but we're getting results out and we're getting cosmology out, and it's really exciting.
Okay, for only the IT, we pushed up against time a bit, and you said that CPUs can cope with this sort of stuff. I suspect maybe you've done a bit too much on your laptop.
I don't know, maybe it's my brain power.
Yeah.